Hey, let's get started. So, good afternoon. How are you doing? Last week, what did you do? Homework, submit homework, read the material. So, let's continue the chapter. We are module 11 here. So, today I would like to talk about more detail the relational database, the story about that. So currently, we based on the relational database, but um, SQL language and then EL diagram and so on and so on. But for logical database design, such as normalization, we need to define and understand the terminologies. Okay, so we will take a look at the concept and terminology and some basic knowledge about relational database. Okay. Mm, there is a topic, and yeah, the assignment 4 and discussion 4 due date is this Friday. You know that. Okay, so keep in mind and then submit by the due date. And then, do you have any question about project? I posted about the project announcement into D2L. This is a document. When you go to the before that D2L and then content browser, left pane, in the bottom side, you can find the folder, project folder, and you can find the description. So this description is this one. So the project title is MJ Innovation Lab Management System. So there are short description, and then the system description you have to implement. So those are like system description. And then based on description, there are three deliverables. So first of all, you have to draw the EL, the diagram. You know what? What is the EL diagram? Like the entity and the relationship. And you can include the relationship between entities. And also includes the modality, the minimum number of occurrence, and cardinality, the maximum number of occurrence, the between relationship. So in order to draw the diagram, previously I introduced the site draw.io. Okay, so you can use this tool or Lucy's chart or any other the tool you can use. But you can use this one, ER relation diagram, something like that. Okay, this is a useful tool for the first task. And then the second task is write a relational table from the task 1. Then you must include the primary key and the foreign key as needed. After that, finally, the write a SQL statement to create relational data table. Okay, and then and the type and constraints of each attribute is up to you. Maybe name for string for name or ID for new numbers or the string. It's totally up to you. And then, if possible, you can add some test data to insert the sample data and then show using the select statement. Okay, so total, this is a task 1 to 3. So you must submit all the code, the SQL code or the source code, and then document the detailing your program and the function, or including the explanation or description. What does that mean? What does that mean? What does that mean? Like that. Okay. So due date of the final project is November 30th. So keep in mind, and then I'd like to recommend you start earlier. And if you have some question, you can ask me. Okay. So that is a project. So any other question about project or schedule? Okay, so let's get into the relational database. So in this chapter, we'll take a look at some basic terminology and the concepts about related to the relational database. Pointer here. So we'll take a look at the terminology, and then what is the relation, and functional dependency, determinant, and then dependent attributes, and then keys, and then normalization, first, second, third, BCNF, and so on. So there are a couple of normalization. So what is the purpose of normalization and the denormalization? Okay, those will be discussed about in logical database module. So anyway, before starting normalization, we'll have to know the basic concept, something like that. So today I'd like to introduce. Okay. So the, the first question I'd like to ask, we have received here, we have received one or more table of the existing data. So data should be stored in a new database. This is assumption. So question is, should the data be stored as received or should be transformed for storage? Stored as received or transformed? What do you think? Yeah, but there's no answer. It's up to you. It depends on the situation. Like you said, if you have already existing database and the new data should be imported, in that case, we have to separate and then some massage to accommodate those kind of the data. But if you have a database, it's a new, it's a empty. In that case, we can store as a received, or if you have any the design concept about database, you can have some massage and then transformed. So it is totally business environment. Okay. This is one of the example. We received 2 table order item. So today I'd like to use this example, these tables, to explain the relational database. And then SKU data, 2 tables. So they can be stored, what is this? Stored in 2 tables, or two tables are combined and then stored as a one table. It's totally depends on the business environment or the current status of the database you have currently. Okay. Okay. And another example table, product, the buyer table, something like that. So in this table, there are three columns: buyer name, SKU managed, and then college major. So you know that what is the SKU? Yeah. It stands for stock keeping unit. So kind of the unique number of the product. So when you go to the Amazon, and then if you check the detail page of the product, there is a SKU, the number. It's kind of unique ID of that product. Okay. So there are three columns: buyer name, SKU manager, that means and then college major. So from this table, we may guess this buyer manages more than one SKU. For example, Pete, the SKU 100, 100, 100, 200, 300. So manage multiple SKU. And also here, Nancy Mayers, so college majors art, and also information system. She has the majors. So to this table, if you add new SKU number to the Nancy Mayer, for example, Nancy Mayers is assigned new SKU 101300. Maybe here we are able to add Nancy Mayer 101300, and then we'll have to fill out this college major. It has a two major: information system, then art. That's why we have to add two rows: art and information system, like this. So maybe a little bit strange and weird. I'd like to add to only one row, Nancy Mayer 101 300, but actually in a table we have to add two rows: art and information system. A little bit weird. Just one input, but actually in a data the table, two rows are inserted, should be inserted. But in that case, we have just only 16 lines, but assume that we have 1 million lines. Actually, the 2 million lines the rows should be inserted into the table. So it doesn't make sense. So you can say that this table is not well designed. Okay, but if you use spreadsheet or Excel, the program, you can create those kind of things. But that table cannot be used in a relational database. So to create the right table, we have to consider several things. Okay. And the relational database model, I'd like to introduce C story of the relational database, the system. That relational database model was introduced in a paper published in 1970, maybe 55 years ago. Okay, so created by E.F. Cote. He was an IBM engineer. And then in this paper, he used the model basically based on the mathematics. known as relational algebra. So what looks like this paper, and that is the paper, the code introduced 1970. So relational model of data for large shared data banks. Okay, something like that. So I uploaded the paper to the detail. So if we have time or interest, not too long. So maybe take a look at, and then what does that mean? Try to understand. So the relational database is begun from this paper. Okay. Okay. And then, so start from there. Okay. And the next, so the IBM Research Center. So the Chamberlain, read, so the relational database research. The project name is System R here. Oh, where is it? This is a project name title. And in this project, the SQL is for the first time designed in this project, early 1970s. After that, the Oracle, that Oracle, the database, the company. So the Oracle released the first commercial database, relational database in 1979, maybe, used SQL. So currently, the Allison, the Larry Ellison, maybe, is a CTO of the Oracle right now. But those three persons are the founders of the Oracle. Okay. And then the IBM, the first relational database start from the IBM Research Center. And 1981, the IBM released the first commercial database, the IBM version. So the SQL language used. After that, the famous database DB2 is released 1983. After that, Microsoft, MySQL, Informix, PostgreSQL, and many the relational database tools and programs use SQL. So the SQL that becomes the de facto standard. Okay, so this is a history. And then this is just for your information. So why relational database was very tempting in 1970, but not easily applicable in the real world because the reason is they relate to performance. So the performance of the database is simply the speed when you send the query, and then how fast we can return the result. Maybe if you send the query less than 1 second, it's good. But if you send the query, it takes about 1 minute or 1 hour. Can you use this system? Nobody use. Okay. So the performance is related to speed, returning the results. But in the relational database, especially the join function takes a lot of resources and consume a lot of time. Okay, so in the 1970s, at the time, the hardware software is not faster than the machine these days. So they know that relational database very good candidate technology, but related to the performance, they don't use too much. But before relational database, the hierarchical and the network database are so popular. They're used in the market. And then the standard, the NC and ISO, the American National Standard Institute information, confused. Published the SQL standards after minor and the major revision. So SQL becomes a de facto standard. So most vendors support standard, but have a slight variation of their own. For example, Oracle top comment is used. That means when you top three, the table, the three from the first, 1, 2, 3, can get the result. But SQL, MySQL, doesn't provide the top comment. Maybe you can use a remit with some statement to get the top three the result. So a little bit slight variation depending on the database system. And then, so important relational model terms: relation, functional dependency, determinant, candidate composite primary key, surrogate foreign key, referential integrity constraint, domain integrity constraint, entity integrity constraint, and normalization, the multi-value dependency, and so on. So you should know what does that mean. Okay. So basically, relational database concept in the database, data appears to be stored as a simple and linear files. Okay. So that's all of the relational database. Just a simple and linear file or table, whatever, we are able to, we are trying to store the data. So these relational database are based on relational algebra, math. You like math? Really? You don't like that? Okay. So the purpose of a relational database, so definition of a relational database is a collection of a relation. So what is a relation? There are many relation. What do you think? What is a relation? Guess what? No? Okay. So anyway, I will explain. Relational database, collection of relation as a group contain the data describe a particular business environment. So store data as a simple and linear file format or table. That is a relational database. It's the beginning concept. So relation. What is this? Simple linear files. You already know that relation. Those kind of the table, the yellow table, general hardware, customer, salesperson, office, what else, and so on. Those are table. In other words, relation. Especially relation is used in the relational database. So-called table. But all tables are not relation. Let me introduce. Okay. So roughly, relation can be interchangeably used, table or file. Okay. And then this is a column, attribute or field, the row, so tuple or record. So interchangeably used. So to create this kind of relation or table, which can be used in the relational database, we have to understand the relation, database relations. So kind of three pages are about database relation, the relational, the algebra. So the first of all, definition, relation schema, capital R. What is this? Set of attributes with their domain. What is the attributes? Hmm? Columns. Okay. If so, what is the domain? Okay. So in the next page, more the detail with the example I'd like to introduce. And another definition is the relation, lowercase r, on relation schema R. So relation, lowercase r, is a set of mappings from attribute to their domain. Okay. And then relation R is a set of n tuple. So A1, A sub 1, D sub 1, A sub 2, D sub 2. So don't confuse, don't be afraid those kind of notations like mathematical notations. Just focus on the meaning. This is not a math class. So focus on the meaning. Okay. So relation schema, capital R, is a set of attributes with their domain. So in other words, relation schema capital R is a set of attributes and their domains. So which means the relation schema define what? Columns of a table. Like Nico said, relational schema capital R define column, age, name, GPA, email address, and course, and what else? And so on and so on. Anyway, so defines columns of a table. So for example, take a look at the student table. If we want to create a student table, first of all, we have to define what kind of attribute we have to add. So for example, student ID, MJID, starting with 983XXXXX, like that. And the name, age, the major. So define the attribute, the columns, that is called relation schema. Okay, it's a meaning. Okay, and then one more thing. is a relation schema. It's a set of attributes, and then domain. What is the domain? So student ID can be numbers or maybe string, but usually numbers. Names, usually string. Age, numbers, integer, specifically. Major, a string. So this is attribute. So here are some set of attribute and their domain. So attribute and attributes domain is the data type, numbers. Name, string, age, numbers, major, string. So schema, relation schema, set up those kind of attributes, and then these kind of domain define two concepts. That's the goal of the relation schema. And then here, what is the relation? Lowercase r. So set up mapping what? Attribute to their value. So attribute, the columns are defined in a relation schema here, like student ID, name, age, major, and the relation mapping. What kind of individual the value should be stored into their attribute. So setting a set of mapping from attribute to their value. So for example, if you have attribute student ID, name, and age, and the major, into this, each column, we mapping the value. In this case, 1001, 1002, 1003. So individual values should be mapping student ID. Alice, Bob, Charlie is a name, should be mapped to name. 20, 22, 19, mapped to column age. Computer science, mathematics, physics should be mapped to the major. So this relation, this is a relations. The specific value should be mapped into the column. Okay, that is the definition of the relation R. That's all. So, make sense? Okay. Then next one is entity. You know that the entity, right? The identifiable the things like customer, computer, student, employee, and salesperson, and so on and so on. It can be an entity. Then take a look at the more detail about the relations. So in a previous page, the relation is a simple linear file or table. You can say that. But there are some conditions. Yeah, okay, here. Before that, relational DBMS product store data about entity in relations. So relation is a special type of table. So in order to be a relation, those 8 characteristics should be satisfied. The row contains data about entity, columns contain data about attribute of the entity, all entries in a column are of the same kind, and so on and so on. So if we have a table and the table, the characteristics are satisfying those eight, you can say that this is a relation. So this relation can be used in relation database. So for your information, relation is a special case of table, but all relations are table, but not all tables are relation. So if we have a table, something like that, relation is a subset of the table. Okay. Then, so integrity constraints. There are three integrity constraints. The first one is the domain integrity constraint. This concept is the same. So it's easy. All the value in a column are of the same kind. It is called a domain integrity constraint. So if you have a relation, it's a table. This is a name. So the second column of the first row, maybe based on this description, names the second. Second column of the first row, relation first name, maybe Christina. And the second column of the every row should be first name. Okay. In this case, Albert, Bruce, Kathy, David, and then it is and so on and so on. Each data in the same column should be the same kind. That is a domain integrity constraint. This is a first constraint. Okay. Okay. Think about that, this table. So there are 1, 2, 3, 4, the 6 columns. Employee number, first name, last name, department, email address, and phone. So that table is a relation or not? What do you think? Yeah. Yeah. So when you take this table satisfies the condition, the characteristics of the relation, the 8 characteristics. So this table is relation. Okay. How about this one? So when you take a look at this part here, how many data? 3. But one of the condition is each column has a unique, no. Is it? Yeah. Cells of the table hold a single value. But here, how many values? 3. So it doesn't satisfy the characteristic. So this is not a relation. It's a table, but not a relation. Okay. And also, there are 2 values. How about this? This is a relation or table? Yeah, 3 phone number. Okay. It's a violates the one of the characteristics. And there's one more. So take a look at the column 100, 200, 300, and 400. Those rows are data about that person, each person, right? But here, blank, 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 blank. So when table is designed, he or she tried to add the fax number and then home telephone number into the like Tom. And also here, this fax number and the home numbers are related to the caldera, right? But one of the example characteristics, the order of the rows are unimportant, which means when you rearrange the order of rows, maybe if this row is rearranged to the rest lines, in this case, we don't know this fax number, to who's this fax number? It is Richard fax number? We don't know. So it doesn't satisfy this condition. The order of rows are important. That's why that this is not the relation, but table, right? And how about this? How about this table? This is a relation or not? There's the answer. What is this? This is a relation. What kind of the special with variable length column value? Maybe this part will be weird, right? A long string, but it is considered treated as a single value. It's a long, but it is a single value. But something weird, but this is the relations. Mhm. Yes. Mhm. Yeah, so for in this cable, the same values like phone number, different the values are stored in this the cell, right? But it's up to you. If we design like in this case 1102, 1191. So this is the first and then the second value. So multiple values are in a cell. So it doesn't satisfy the one of the characteristics of the relation. But if you uh, create those phone number as a string, like this, and then add this string into this, the cell, makes sense. But think about it, why we use the database. The basic purpose is to ask something and then get back as soon as possible. But in that case, if you return this phone number, we need to add one more operation to parse this string and then split by the comma. So we need another operation. We can do that, but it's an unnecessary operation related to the performance. So not a good design of the database table. Okay. So, but take a look at this one. Just comment join the account department in the March. We don't have to split that string. Just this message, oops, these values gives one the meaning. to users. Okay, we don't have to split like this one to get the meaningful value. Okay, so a little bit weird, but this is a relation with the variable length column. Make sense? Okay. So this is a table, relation, file, column, attribute field, row, tuple, record, interchangeably used. So, oops, yeah, go on. Okay, then next one is, the paper published by the court. So in his paper, the laws of the relation must be unique in their paper, in his paper. And then there's no requirement for designate primary key. So that means the requirements for unique laws implies primary key can be designated. So in the paper in 1970, there are rows that each rows are unique. So that implies that one looks like as the primary key. But in real world these days, you know that every table, every relation has a key, primary key. Right? So we are able to select primary key. In other words, when do we designate the primary key? In order to do that, we need some procedure. So important concept in the relational database, functional dependency. So what is a functional dependency? The functional dependency occurs when the value of one or a set of attributes determine value of a second or set of attributes. What does that mean? Think about this example. In order to calculate cookie cost, we have to know what number of boxes. From this equation, relationship, the, the cost of the box is $5. So to get the total cookie cost, we have to know number of boxes, maybe five times five, $25. 10 times five, $50. So from this description, you can say that here, cookie cost depends on number of boxes. Make sense? In other words, cookie cost functionally dependent on number of boxes. It's the same. So we are able to write like this using arrow in a functional dependency, which means cookie cost functionally dependent on number of boxes. In other words, number of boxes determine cookie cost. The same description is just the same meaning. Make sense? Okay. And then the left side, functional dependency, in this case, number of box is called determinant. Number of box, determinants, cookie cost. Okay. So how about this? Extended price can be calculated by multiply quantity and the unit price. Okay. From this relationship, extended price is functionally dependent both quantity and unit price. In other words, quantity and unit price determine what? Extended price. So quantity and unit price are called determinant in this relationship. Make sense? Okay. How about this table? There are three columns: object, color, it's a color, weight, the shape. Think about that. Here, there is a description. If your friends look into the sack, see the object and tells you the color of object, you can tell her the weight of the object. So if Christina pick one red color, and then you can say that that is weight is 5 pounds. And then if you choose blue, it's 5 pounds. Yellow, it's 7 pounds. So the weight is functionally dependent on what? Color. In other words, object color determine weight. So object color is what? Determinant. Mhm. Mhm. And then how about the shape? If you know the color, you can say that the shape. Choose red, it's a ball shape. Blue, cube. Yellow, cube. Similarly, color determinant shape, right? So from those two functional dependencies, you can say that the color determines both weight and the shape. Make sense? Previous example is based on equation like this. Quantity multiplied with the unit price is an equation. So functional dependency can be used in equation relationship, or this table is not an equation, but functional dependency also used. Mhm. Mhm. No, there's an yeah, just we can say the functionally dependent. Mm. So important concept is a determinant. So determinant is related to the key. Okay? So left side is called the determinant right now. Okay. And then one more, the algebra. So composite determinant means a determinant consists of more than one attribute. Think about that. In order to get the grade, we have to know student number and then class number. Student number 983-11111, class number CSCI 3245, maybe grade A or B, right? So this is a composite determinant. And then there's some kind of a rule, dependence rule. Determinant A determines B and C. In this case, you can say that the A determines and B and A determinant to C. This is a decomposition rule. So this one, the color determines weight and the shape. In other words, you can say that color determines weight and color determinant shape. This is a decomposition rule. And then vice versa, this is a union rule. A determines a B and the A determines C. You can say that A determinant B and C. This is a opposite concept, decomposition rule. This is called the union rule. And the last one, determinant, there are two composite determinants, A and B, determinants C. So neither A nor B determines a C by itself. In this case, yeah, here. Student number, this is A, plus number B, grade in the C. So in order to get the grade, we have to know A and B. Without B, student number, which course grade? Without student number, you know, database principal course, which student's grade? We don't know. So in this relationship, we have to know both A and B determinant to get C. Okay, this is a relationship. Okay, so take a look at the more actual example. So question is, does any column determine the value of another column? So question is this one. If we know the value of department, this is before that, this is a table relation SKU data. The columns are SKU, stock keeping units, and stock keeping unit description, then department, and then buyer. There are 4 columns, and then rows, something like this. So question is, if you know the value of the department, can we determine a unique value of a buyer? What do you think? If you know determinants, the department determines buyer. Hmm? Mhm. Yeah, no. The answer is no. Why? For example, the water sports determinant associated with what? Buyer, Pete Hansen. But when you take a look at the other rows, water sports is also associated with what? Who? Nancy Mayer. She means water sports is associated multiple the values in the buyers, Pete and Nancy. That's why department does not functionally determine buyer. Make sense? So how about SKU, stock keeping unit? Determine SKU description, department, buyer. So for example, 1000100, this one. So fortunately, this is a unique. So determine the yellow, standard scuba tank yellow. And then department is the water sports and the buyer Pete Hansen. Only unique. So SKU determine description, department, and the buyer. Make sense? Right? How about description here? Description determine SKU, department, the buyer. Maybe half-tone tent is a unique. Half-tone tent determine 201000. And also associated camping, only camping. And then the buyer, Cindy Law. The only associated only one value, unique value. So you can say that SKU description, determine SKU, department, and buyer. We have the two functional dependency relationship. How about the buyer? Buyer determines department. What do you think? The buyer here, for example, Pete Hansen from first line to there. Pete Hansen is associates what? Water sports. Only one value is associated. Nancy Mayer is associated what? Water sports. Only one water sports. Cindy Rowe associates camping. Jerry climbing associates only one value. So can say that buyer determinant department. Mm, 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 mm. Mhm. It's based on this table. Mhm. If so, buyer is associate SKU description or SKU? What do you think? No, why? Pete Hansen. Pete Hansen associate yellow, magenta, light blue, dark blue, something like this. Associate multiple value in a department. So buyer doesn't determine SKU description. How about SKU? Pete Hansen is associate 100, 100, 200, 300, 400. Associate multiple value in the SKU. Not unique. So buyer doesn't determine SKU. Only buyer determines department. Like that. So from this table, we have the three functional dependency relationship. SKU, determinant, SKU description, determinant, buyer, also determinant. Makes sense. How about this? The order item table. There are 5 columns. Order number, SKU, quantity, price, and extended price. So question, the order number determine SKU. What do you think? Order number determine SKU? Why? Right. It's also multiple SKU 000, 201, 000, 202, 000. So here, the order number doesn't determine SKU. How about SKU determines order number? No. The reason is that 101, 100 determinant associated 2000, but same SKU here associates 3000. Not unique. Associated multiple values. So SKU doesn't determine order number. So in this table, to keep an accurate record to warrior customer, actually, not this one. In this case, we have to create composite determinant to determine every other columns. So order number and SKU, if you use 2 columns as a determinant. So order number SKU, determinant quantity, 1000, 201110. This is unique, right? Determinant, quantity, price, and extended price. So can write the first functional dependency. In that case, order number and SKU are composite determinant. And also, quantity and price determinant determines extended price. Makes sense. So we have second relationship. What do you think? Quantity and price. Quantity and price determinant determines SKU. What do you think? Why? 1 and 300 associate 201000. But here, 1 and 300 is also associate 100200. Multiple values are associated. So quantity price does not determine SKU. Okay, so we can have those two functional dependency. Then so have to tempting. So this is a previous table, SKU data, the determinant, SKU description, and the buyer. So SKU description, and then buyer. So you might think, for example, 100100 appears once in this SKU column. And also help content appear just once. So sampling conclude that values of the determinants are always unique in a relation, but it is not always true. The reason is that the buyer is a determinant, determines the department, but it's not unique. The reason the Cindy row appears 3 times in a row in a buyer column, but still associate one value camping, but appear 3 times, not just one. Make sense? Okay. So as a result, SKU determines all other columns. We already drive. SKU determines all other columns. Description, department, and bio. Description also determines all other columns, SKU, department, and bio. Okay, like this. But buyer doesn't determine all other buyer, only determines department. No SKU description and no SKU. Okay? And in this case, order item, order number, and SKU is a determinant. And then quantity and price is also determinant, like this. So those two composite determinants determines all other columns, quantity, price, and extended price here. But quantity and price only determines extended price. Okay. So it doesn't determine the other columns. Okay. Then, hmm, so we cannot, important, cannot find the determinant of all functional dependency simply by looking for unique value in one column. There are some reasons, just two reasons. One is that data set limitation. In this example, we have just 7 rows, but think about the 1 million, 2 million. We don't know. Maybe SKU cannot determine quantity. We don't know. Or in this table, SKU, maybe standard scuba tank yellow, so 1 million lines number. It can have the different, maybe 999 value, something like this. We don't know. So the data is limited. This is one reason. And then must be logically determinant, which means that relationship makes sense. For example, student ID determines name. Makes sense. Like 983-10100 is related to only one student, like Joshua. If there's no 2 person with the same MJ ID, only one MJ ID is associated to Joshua. So that one should be make sense. How about vice versa? Name associates student ID. Joshua, maybe Joshua A, Joshua B. If possible, 983-10100. But this is Joshua A. But another student, Joshua B, can have different MJ ID. So it doesn't make sense to reflect the business environment. So logically, should be logically make sense. Okay. So the best strategy to get those functional dependency, analyze the business environment, or ask users, the internal user, staff, or faculty, students, to understand fully in detail the business. Okay, so this is the last one, the key. So why the determinant is important? Determinant is related to how to select the key. So key is definition is a combination of one or more column used to identify particular row in a relation. You already used primary key, the foreign key, in the example of the SQL, the statement. Okay, composite key, you know that consists of 2 or more columns, like this, or the number SKU, something like that. Okay. The candidate key determines all other columns in relation. So this is important. Determines all other or the other column. From this example, there are 3 determinants: SKU description, and then buyer. SKU and description determines all the other columns: description, department, and the buyer. SKU, department, buyer. That means those 2 can be your candidate key. How about this? Buyer. only determines department, does not determine description SKU. So it cannot be a candidate key. So you can choose candidate key out of determinant. How about this one? Order number and SKU determine all the other columns, quantity, price, and extended prices. So it can be candidate key. How about this one? Quantity and price. Quantity and price only determines extended price, doesn't determine SKU and order number. So it cannot be a candidate key. So to select after that, you can choose primary key out of candidate keys. So primary key is a candidate key. Select as a primary means of identifying rows in relations. So if we have a table or relation, we select determinant. And then from determinant, we select, this is a determinant. Select candidate key. And then out of the candidate key, you can pick primary key. So this is the relations. So in a simple table, you can take a look at the column. This is the primary key, but more complicated table, lots of columns, lots of row. We don't know which one can be a primary key. So we take steps. First, select determinant, and then select candidate key out of determinant. After that, choose primary key from the candidate key. This is a procedure to select the primary key. Okay. Sorry, over. So that's all today. Any questions? Nothing? Okay, thank you. And then have a great day. And then see you next week.